Good afternoon, and welcome to TME Presents Sustaining Contingency Bases Through Solar Power. You've read the article, now learn the rest of the story. I'm Daniel Wheatley, Associate Editor for the Military Engineer, and it's my pleasure to welcome you here today. Before we get started, though, I'd like to go over a few items so you know how to participate in today's event. All attendees are in a listen-only mode for the presentation. You can submit questions for the presenters at any time using the questions pane of your control panel. We will collect these and address as many as we can during the Q&A section at the end of the presentation. Please also submit any technical issues you may be encountering here as well. In 2009, the Government Accountability Office recognized the massive cost of fuel use at forward deployed locations, placing the minimum fully burdened cost of fuel at $15 a gallon when logistic concerns are included. The fuel logistics issue creates a potential threat to forward operating base energy resiliency. If fuel convoys are cut off, attacked, or depleted, base electrical power to mission essential operations is lost. Additionally, fuel convoys requires security protection, which places personnel in harm's way. A study from the Army Environmental Policy Institute showed that in dangerous environments such as Afghanistan, there was one casualty for every 24 fuel convoys. Research within the U.S. Air Force demonstrates that renewable energy systems may be viable candidates for contingency bases and are reasonable from economic and logistics perspectives in relatively short time spans when compared with typical forward operating base lifetimes. This webinar will cover ongoing research in reliable and cost-effective renewable energy sources for forward operating bases and other remote locations. And I would now like to introduce our article author, Major Nathan Thomsen, PE, the Air Force Institute of Technology, for a deep dive into the research behind the article. And joining him today is Dr. Torrey Wagner, also with the Air Force Institute of Technology. So, Major Thomsen, the floor is yours, so please take it away.
Thanks, Daniel. As Daniel said, I'm Major Nathan Thomsen. I'm a civil engineering officer at Tyndall Air Force Base at the Air Force Civil Engineering Center, and I'm going to be talking to you a little bit today about my thesis research, which I conducted at the Air Force Institute of Technology. And I'm joined today by one of my professors who assisted a bunch in and actually kind of initiated this research effort, and that's now retired Lieutenant Colonel Dr. Torrey Wagner. And I'll let him tell a little bit about himself to you.
Hey, can everyone hear me? I'll do the audio check now.
Absolutely, Dr. Wagner.
So thanks, Major Thomsen. I initiated in a DoD energy stream of research at AFIT 3 years ago with the support of the Operational Energy Office of the Air Staff. Major Thomsen was one of the students in my first energy class and really excelled above and beyond the typical student effort. I think his MATLAB-based modeling and optimization of energy systems shows how order of magnitude improvements in the cost or performance of batteries and photovoltaics is making them more of a candidate to meet DoD energy needs. And this is something where I say more of a candidate because clearly they're not going to meet every DoD energy need on the battlefield, but there are more and more applications where they are now becoming viable. And so the research that you'll hear about today is one of those applications where this is a candidate for commanders to think that, hey, this could be an option to increase the resiliency of my base. So that's all that I wanted to say. Major Thomsen, back to you.
Thanks, Dr. Wagner. And I also wanted to recognize Mr. Reza Salavani. Also from AFCEC, he was the sponsor for my research and was supposed to be joining us on this webinar today. Unfortunately, both of us are calling in from Panama City, Florida, and luckily I haven't been touched by the water yet, but he's got about 6 inches of water affecting his home right now. So he's taking care of that right now, understandably. And if we can go to the next slide now. So the research objective of my thesis and what we're talking about today is looking at renewable energy systems and how they can possibly perform as replacements for large prime power generators at remote locations. And we'll go over what some of those different types of remote locations might be. Next slide, please. And also like to acknowledge the rest of my thesis committee from AFIT as well as from Battelle, and then our 2 research sponsors, which was the Air Force Civil Engineering Center down here at Tyndall Air Force Base, as well as the Air National Guard Civil Engineering Technical Service Center. They both sponsored this research. So I want to start with a question, which is sort of a theoretical question to think about. Would you rather have to move 100 tons of whatever material that you're going to have to use and pay $10,000 today, or would you rather have to move 10 tons and pay $1,000 every month from now on? And of course, the answer to that question is it depends. It depends on a lot. What are we moving? And especially what is our time scale? And so that is a question that is going to be faced by every engineer and designer who wants to look at replacing traditional non-renewable energy systems. The question is, do we want to pay that extra upfront cost and that extra upfront potential logistics challenge in order to make up for long-term savings, long-term logistics improvements? And so we'll reapproach this question at the end, but just something to consider while we're talking about renewable energy systems. And so overview of what we'll be talking about today. First of all, want to start by talking about the motivation for why the DoD and other remote locations in general would want to move away from generators and onto something more renewable. Next, we'll look at the first paper that we published, which was examining just how viable are solar renewable energy systems, so photovoltaic renewable energy systems, to replace generators. And then next, we expanded that model by looking at the whole optimization method and how we can optimize not just for cost, but also for minimum logistics. And we'll sort of explain later what we're talking about by logistics later. And then last, I want to conclude by talking about what are the applications and significance of this research by looking at a few different case studies. So what are these remote locations? So just to give 3 examples, there are many others that could be, for instance, isolated construction sites or disaster relief camps. But here's just 3 examples of locations that are currently faced with serious logistic challenges while they're operating on diesel generators. So the first is in Northern Ontario, there's a 15,000 person Arctic community, and every year they're using 6 million gallons of fuel and releasing 65,000 tons of CO2 just to operate their small power grid. And that cost is $28 million, quite substantial for such a small community. There's the example of remote Pacific islands. And because these islands have such small economies and because their power grids are operated entirely on diesel fuel or other heavy fuel oils in order to run their electric grids, energy cost is a large portion of their GDP. And so you can have their economic health really determined by the price of oil. So If the price of oil goes up, unfortunately, their economy is negatively affected, and if it goes down, then they're able to operate more efficiently. And so, obviously, being tied to the cost of diesel fuel, having your entire economy tied to that is not ideal. And then finally, we have our focus here for this Air Force research is military forward operating bases, or FOBs, sometimes also called contingency bases. And during the heights of the Iraq and Afghanistan wars, we were delivering over 2 million gallons of fuel per day to different FOBs in both those locations. And to give an example of how extensive that can be for even a small 600-person base, you're going to have to deliver 22 trucks a day. And not all of those are going to be fuel, but a significant portion of them are going to be fuel. And obviously, fuel being a flammable resource, it can be one of the most dangerous things to transport. In fact, there was one study that showed that in Afghanistan, the coalition had 1 casualty for every 24 convoys. And so if you're able to reduce the number of fuel convoys, you're actually able to reduce the number of casualties in the deployed environment. So obvious reasons why the military should be looking at methods to reduce logistics challenges. And so, as Daniel mentioned, in 2009, we had this Government Accountability Office report, and it priced out the fully burdened cost of fuel, which includes costs like transportation, storage, and actually using the fuel. That's much more substantial than the price we pay at the pump here in the continental United States. And they priced it starting out at a minimum of $15 per gallon, which obviously is quite substantial. And we have to put that in line with the fact that our fuel use in gallons per person deployed per day has increased in every conflict the U.S. has been involved in since World War II, on a pretty linear increase there. And Operation Iraqi Freedom and Operation Enduring Freedom in Iraq and Afghanistan have been no exception to the rule. And so we continue to see that fuel consumption continue to go up. And so this increasing fuel consumption and the fact that we're paying so much for the fuel is obviously a substantial economic factor, but it's also a huge logistics factor. And that logistics factor causes it to be a risk to our energy assurance on these deployed bases. And so we put this research in the light of recent DoD policies on renewable energy. And these include 2018 National Defense Strategy, which looks at rising near-peer threats. Those are large nation states that is going to sort of change the environment of our warfare. And so currently we've been able to operate with sort of 100% guaranteed air superiority, and our fuel lines operate mostly unprotected and with really no threats. However, that's going to change facing a near-peer adversary. Next, DoD Instruction 4170 for installation energy prescribes that we should use renewable energy when it's shown to be cost-effective or to enhance energy resiliency. We've got the DoD Strategic Sustainability Performance Plan for 2016, which argues that we need to assure the continued availability of energy through our reduction of fossil fuel use. And lastly, the Air Force Energy Flight Plan, which prescribes 3 different goals that the Air Force is looking towards in light of energy, which is to improve our resiliency, optimize demand, and ensure supply. And renewable energy can actually be part of all 3 of these. It improves resiliency by eliminating that logistics risk factor, optimizes demand by reducing our demand for fuel and other energy at the point of use. And finally, it assures supply by switching over to a non-traditional asset for energy. Since we're not relying on that fuel system, we can sort of cut that part of fuel demand from the supply that we need to assure. And finally, it argues that we need to promote, develop, and utilize clean energy technologies as part of the Air Force energy supply. So I think, Daniel, do we have those poll questions?
Yes, we do.
We want to ask the one now about everybody's background on renewable energy. That'd be great. So how would you assess your familiarity with renewable energy systems? If everybody can answer that here, and so we can kind of get some feedback on where everybody's coming from.
All right, we've got some good answers coming in. I'm going to give it just a little bit more time here for people to vote. And close it in 3, 2, and 1.
All right, looks like we've got quite a bit of experience, but definitely a good portion, probably 75% who haven't worked with it extensively. So it's a good background, and definitely in the question and answer session at the end, definitely looking forward to some of those questions. And hopefully this can give everybody a little bit more background into at least one type of renewable energy in terms of solar PV. So as engineers, we can look at many different types of renewable energy sources, right? We have wind, solar, hydro, biomass. And so most of these renewable energy sources, if we use them, it can potentially eliminate our need for our fuel resupply and generate energy self-sufficient sites, which obviously for, say, remote FOBs or isolated remote civilian locations, that's hugely attractive for those locations, basically cutting off their need for energy supply chains. But the question is, if we're talking about a truly remote location or a military FOB, what type of renewable resource should we look at using? And for this research, if you can go to the next slide there, Daniel. For this research, we recognize solar photovoltaics, or PV, as probably the best resource that the DoD can utilize. And part of that reason is just historical, and that's that right now, solar is the fastest growing renewable energy resource. In 2016, which is just a couple of years ago, obviously, but there was a 50% expansion of PV in that single year alone. And we also see that the cost of photovoltaics is declining rapidly. The National Renewable Energy Laboratory has projected that in just a few years, the price will drop to 20 cents per watt, which is quite impressive. But when we're talking about a remote contingency base or a remote civilian location, there's some other reasons why we would need to use something like solar, and that's based on really the fact that it's portable and that it eliminates our energy supply chain by allowing us to generate our own power. And you look at options like, for instance, wind. The issue is that just those large turbine blades really are not portable, and they're not transportable to the location of use. However, PV systems, we see that those are. And obviously, because we're generating our own power from them, they are going to reduce our power supply burden versus things like micro turbines, which could be a great idea for DoD FOBs. However, it's not going to reduce our use of fossil fuels, at least not prevent it completely. And so based on all this, we chose to look at solar PV for all our research here. And so my research was divided into 3 different research questions. And the first one was to just look at, is renewable energy realistic to use at a remote location for power production? And the second question, what would be the most efficient and effective design for that system if we were going to optimize it for cost, logistics, and performance requirements, and specifically looking at that logistics piece. And lastly, how would implementation of the system affect remote location power resiliency? Hopefully I've started to answer that last question there, which is just that if we're able to move towards a sustainable resource, we no longer have this logistics supply chain, which is a potential threat to our power resilience and mission assurance at those locations. So next, I'd like to go talk about answering that first question, looking at the viability of PV to replace generators at these remote locations. And so this first paper, we developed an initial model to test what a solar renewable energy system would look like at a remote location. And so this research was published in the International Journal of Energy Production and Management, if you're curious. So our case study for this was we picked a FOB, just a fictional FOB in the Helmand province of Afghanistan. And we looked at assuming that it's powered by currently a 800 kilowatt Air Force Bear power unit, or BPU. And those can operate on diesel fuel or JP8. Obviously, that's helpful for the military. And they're worldwide transportable via airlift, although they're quite heavy. And we wanted to counterpose that with a potential replacement renewable system that's going to be a fixed tilt PV array with lithium ion battery storage and a DC to AC inverter, and with a goal of producing 800 kilowatts constantly, which is, the goal of that is just to match sort of what this generator can produce, which is obviously difficult considering that solar power changes with time. But that's what we wanted to model. We wanted a sort of a difficult problem to solve with PV. And so we started by looking at Marja in the Helmand province, what is the power available? And that top chart there just shows you the power in each hour of a typical solar year. And it averages out to 240 watts per square meter, average out all the time. So obviously your peak during the daytime is going to be much higher than that, but at night you're not going to get any power. And so if you average out per hours of the year, it's about 240 watts per square meter. And you can see the energy intensity is shown based on hour of the day on that bottom chart there. And you can see during the winter, even somewhere like Afghanistan, periods like November, December, January, and February, during the winter there, they have a lot more cloudy weather, and just the inclination of the sun affects our ability to capture energy. So when we're developing a renewable energy system, a lot of the focus is on optimization. How can we optimize this system? And optimization, a lot of it is based on how do we develop and size our system. And so in the case of this system, we have both a solar array size and a battery size. And so this graph here is just showing a very simple optimization where we can start with a very large battery size, which allows us to have our minimum possible solar array size. And then as we reduce our size of battery, we have to move up our solar array size. Or you could look at it the other way. As you increase your solar array size, you're going to have to store less energy since you're producing more power. And so overall, since lithium-ion batteries and any type of energy storage is so expensive, the larger we can increase that solar array, the lower our cost is going to be until we reach an optimum point right here, right in that 14 to 1500 kilowatt range. And so that demonstrates sort of what we're looking at in optimization. However, once you start looking at logistics and performance concerns, you're going to have multiple trade-offs. And that's what this slide is showing. So if you look at that right half of that slide here, we have all the different possible battery capacities we could choose and all the different PV sizes that we could choose. And in this upper right quadrant, we have an area where this generator is going to produce power for 100% of the time. And as we move down to the left, we're going to increase our number of hours not met, or that's our failure criteria, when basically we're going to lose power. And so we're actually able to make a significant cost savings, and cost is demonstrated by the colors on the left side of the chart, by moving from 0 failure hours to 1% failure, or sometimes we call that LPSP, the loss of power supply probability. And so we actually look at somewhere around $23 million for out in this range, down to about 18 million for the cost of this system, which is significant when we're talking about replacing a single generator, although the BPU itself is fairly expensive. So we also wanted to look at logistics. So how much space are we going to take up on aircraft, or are we going to take up in transports, and how much weight are we going to have to actually move in order to get this renewable energy system in place? Obviously, PV panels and batteries take up a lot of space. And what we realized from looking at this is that our optimum system, they're optimized for 1%. And actually, I should say the reason that we picked 1% for the failure criteria is that that's right around the same amount of time that a typical generator is going to have to be taken offline just for preventative maintenance. So not counting unplanned issues, just any generator that you have, at least 1% of the time it's going to have to be taken down so that we can change the oil and change out any parts that have worn down. And so we wanted to simulate that with our renewable energy system. And so that solution is shown here in this red dot. And I think it's cut off a little bit, at least at the bottom of my screen. But what we found was about a 3,000 cubic meter transport volume and 500,000 kilograms, which is definitely substantial for this renewable energy system. It's about 27 times the volume and 50 times the weight of a traditional generator system. And that may seem like a challenge that we're just never going to get past with renewable energy. But when we look at it from a life cycle point of view, looking at the life cycle cost, which costs are shown in these solid lines here, in less than 2 years, we reach our cost payback point, which is pretty impressive for replacing this entire system in under 2 years. But what's more impressive than that, if you want to look at logistics in terms of weight transported, and that's shown in the dashed lines here, our crossover point for logistics in terms of weight is actually going to happen in just over 100 days, which is quite impressive. And that, I think, is the thing that was most staggering about this research, is that if we're looking in terms of logistics, this might be one of the best ways we can reduce the total amount of weight that we have to transport. And where does all that weight come from? It's almost entirely from fuel. You can see that it starts out almost near zero from the generator. It's just the issue of moving all that fuel. So next, I'd like to cover the next 2 papers that we published that we're looking at or are scheduled to be published, and that's looking at how can we define this optimization criteria, specifically in order to minimize logistics. So we did a pretty detailed literature review to look at what else are folks researching right now in terms of logistics. And obviously there's a ton of research, hundreds of thousands of articles that are on renewable energy and PV renewable energy systems. But of those looking at logistics, there really is not many out there. And so out of 58 articles that we surveyed over the last couple of years, we found there was only one, and that was actually the first paper that we published. So logistics have just kind of been sort of left out of looking at these renewable energy systems. And part of that's, if we're going to put up a PV array in California, we're not worried as much about even how much it costs to transport it there. But now in the middle of the mountains of Afghanistan, transport of those PV arrays and the energy storage is going to be a huge, huge factor. And so we decided to propose these different key factors that we wanted to look at when determining how to optimize PV renewable energy systems at these remote locations. So the first was reliability. So we wanted greater than 99% uptime. That's that 1% loss of power supply probability. And obviously initial cost is always going to be a factor for the military or civilian groups, even NGOs. Cost is always going to be a factor. And then last, we wanted to add logistics. And so we proposed that we could divide logistics into 3 different components. And so this is your land area of your deployed PV array in meters squared, your weight that you need to transport in kilograms, your stacked volume for transport. So all your PV panels would be stacked as densely as you can pack them, along with your energy storage. And all 3 of these sort of compose logistics. And so using this model, the first thing that we chose to do was to look at just the photovoltaic modules themselves and how we can pick the right one based on optimizing for logistics. And we actually submitted this paper to this conference, which has since gone virtual, unfortunately. But of course, can look out for the real conference to happen next year. So in terms of the PV modules themselves, we wanted to look at the cost, the module efficiency, the area of PV that would be required, and the PV panel weight density. And so most of these things that we're looking at are in terms of power density. So we wanted our area density, which could also be considered your efficiency in watts per meter squared, your weight density in watts per kilogram, and your volume density in watts per cubic meter. And again, that's for transport. And of course, your initial cost is going to be a major factor. And so we looked at 29 different solar cell modules, 18 monocrystalline, 6 polycrystalline, and 2 heterojunction. Those are HIT modules, which is a combination of crystalline silicon as well as amorphous silicon in a multi-junction configuration. And we also looked at 3 different experimental solar blankets. And they're not shown on the graphs that we have just because the cost made them completely uneconomical. So we talked about that we're starting to approach close to 20 cents per watt. And these are instead at least $6 up to $100 per watt. And so using a manufacturer's data, we charted these out, and you can see here that there's a very slight increase in maximum efficiency based on cost. But that cost is very significant. So going from right around 60 cents a watt up to $1.50 per watt maybe gives us 2% efficiency gain. So because of that, what seems to be the most economical option is definitely monocrystalline here. And I'll show you that again on the next graph. And so this 3-dimensional graph, we were able to look at the power weight density of each of these modules, along with the volume density and the cost per watt. And you can see an ideal PV module would be located somewhere there in the center top front of this diagram. And of course, there aren't any modules there. So we had to pick one that made a reasonable trade-off. And so we selected this monocrystalline module just because it was one of the lowest cost modules, and it showed a great weight power density. However, the volume power density was more or less just average. So that's something to consider. The selection is going to change based on your logistics priorities. And so we determined that logistics is an important consideration when selecting PV modules in terms of their area, volume, and weight power densities. And we proposed that low-cost monocrystalline panels would be the best candidates for these remote locations. In the future, thin film blankets are definitely showing their advantages, just because their power, volume, and weight densities would probably be substantially better, but the cost just makes them uneconomical when compared to traditional PV modules. And lastly, we'll go into here how we want to develop this optimal PV index. And so, unfortunately, just for the scope of my thesis, I wasn't really able to focus on the energy storage choice. And obviously, you're going to have similar trade-offs as you did with the PV modules when you're selecting your choice of energy storage. And really, we were confined to this range here, simply because we had to look for right around that 1 megawatt power rating, since we're talking about replacing an 800 kilowatt generator. And because you have cloudy days, and obviously every night you're going to need to power your remote location, you really need a storage device that's going to be able to hold up for days or really several days at a time. And so that pushes you right into this range where we have batteries and fuel cells. And the issue here, shown in color, is your efficiency. And the issue with hydrogen fuel cells is that they're only 30 to maybe 50% efficient. And that really is why batteries just are much more efficient. Right now it's showing that it's 70 to 85% efficient, but the round trip efficiency continues to increase, especially for lithium ion batteries. And that really led us to select that for this study. And so we have a third paper that's in the authorship process right now that wants to demonstrate this logistics optimization method that we can use for these renewable energy systems. So what is that optimization method? And we wanted to look at a multi-criteria optimization method that looks at these different variables. Obviously, we already talked about performance and reliability, and that's just setting a constraint on your max loss of power supply probability, or your reliability of 90%, 99% or greater. Economics, we wanted to look at lowest initial system cost or life cycle cost. And then we have the logistics factor. And so logistics, as we defined it, was your land area of PV and your transport weight and transport volume for this renewable energy system. And so each of these, you're going to have to define a score, which we just looked at scores going between 0 and 100 within the search range of all the different possible combinations that we could look at, with 100 being the heaviest and 0 being the lightest possible. And then we assign an importance or weight to each of these three components: your area, your weight, and your volume. And as I'll show later, you can change your logistics index focus based on the location that you plan to use the renewable energy system. So using this optimization method and plugging back in slightly upgraded version of our Afghanistan FOB model, you can see here that shown in black, these black lines here is your 1% probability, 1% loss of power supply probability, so 99% uptime curve there. And so all of your solutions, sort of your optimal solutions, are going to lie somewhere along that curve. Anything to the right of that curve, you're going to be sort of spending extra money or extra logistics cost on, and to the left of that curve, it's just not going to meet your reliability requirement. And so we looked at 5 possible different options for how you might optimize this system. You could optimize for cost or weight, which are pretty similar. They choose sort of a medium value where you want a medium-sized PV array and a medium-sized battery. But you could also look at optimizing for area, and you're going to pay a huge cost in terms of requiring just a much larger energy storage. And obviously, lithium-ion batteries are very expensive. But that would be an option. If you're very constrained in your area that you can take up, you may want to sort of slide all the way to the left end of this curve. And then if we want to optimize for sort of a customizable balanced choice, that's where we would use this logistics index. And for here, we selected one that takes into account both the area that you're going to take up, well, actually all three, the factor of the area that you're going to take, your weight, and your volume that you're going to have to transport. And so what this shows is that there's just a lot of different options that renewable energy system planners can look at. And obviously there's going to be trade-offs. So this again shows a Pareto curve looking at 1% loss of power supply probability. And we have our logistics index mapped here along the bottom. So towards the left, we have our sort of smallest systems or lightest systems that we'll have to transport, and to the right, heavier systems. And the lowest cost point is actually going to be using the most logistics. But that's our absolute minimum cost point. And you can see that if we're willing to spend just maybe 5% more, we can actually move to our optimum logistics point. And so that's an important trade-off for renewable energy system planners to look at. For a very small cost difference, we're able to make a pretty substantial change to the amount of logistics that we're going to have to transport. And obviously, you can make a different trade-off. For instance, if cost was really important, but maybe you cared about logistics, you could spend just a slight premium more and move all the way down to a logistics index of 34. So another issue that you definitely want to consider when you're looking at renewable energy systems is hybrid renewable energy systems. And what those are is a renewable energy system where you connect a diesel generator to it. And so anytime that your renewable energy system, your PV array, is not able to meet the load, your batteries run empty, then you'll turn on the generator and run it. And so shown in blue here, you can see as you increase the amount of load that you can provide by the generator, you can decrease your size of your renewable energy system, and that lowers your cost. However, if you add in the fuel cost for running that generator, the line actually becomes this green line here, where the more we decide to use the generator, the more our overall cost of system increases. And so we can sort of optimize both those trends by picking the hybrid renewable energy system, which is shown in that red line there. And effectively, we're able to reach a minimum cost point where it's right around 5% of the load that would be provided by that generator. And so we're able to significantly downsize our renewable energy system. But at the same time, that generator is only going to operate 5% of the time. And so this might be something where from a cost perspective, it's probably more efficient typically to use a hybrid renewable energy system than it would be to use a pure renewable energy system where we don't have a generator, at least that we're planning to operate on. And so the next thing I want to cover is just sort of some case studies for where this could be used and how we applied the model to those different case studies. And so here's the three that we looked at. The first was that Helmand Province, Afghanistan FOB that I showed before. And you can see that the logistics weights we chose were very balanced here between weight, volume, and land area. The results for that we've kind of already shown, but I'll hit on them again in a minute. And then what I want to do here is compare these two other more civilian locations. So Puerto Rico obviously has gotten hit by a couple bad storms, and it's a pretty remote location. And so the price of fuel is going to be higher than, say, a traditional location in the continental United States. But they also have reasons why they would want to be sustainable away from diesel fuel. But because they're transporting everything on the island has to be transported by ship, really volume would be their biggest transportation concern, along with land area, just because it's an island. And anytime you have an island, your area of cleared land without foliage is going to be limited. And then last, we looked at a African village where this is just a remote location in South Sudan. And there, your cost of fuel is going to be lower than, say, a remote island, but it's still going to be higher than downtown Houston, for example. So because of the fact we need to transport everything out to these remote locations, probably on tractor trailers or potentially aircraft, that's where weight comes in to play. And so I'm really trying to minimize the weight versus volume or land area, where in the middle of the desert of Africa, there's plenty of room for PV arrays. So the goal there was to minimize the weight. And so here you can see for that Puerto Rico island scenario and the Sudan African village here, these two different scenarios. And again, we have these 5 different choices that we can make based on what is our priority. And you can see the biggest difference that I want you to notice is just the different logistics index locations. Because on the island scenario, we were focused on minimizing that PV array size, even if we had to pay a premium for it, that shifts our design point to the left, meaning greater battery capacity and a smaller solar array size. Versus at the African village, we are not as worried about the size of the PV array. We're really only worried about weight, and batteries are very heavy. And so that shifts our optimum logistics point to the right. And so we're going to have a larger PV array and smaller batteries. And so this just demonstrates how we can use this logistics model to make 2 different choices for 2 completely different locations. And in these locations, we used different power demands and different, obviously they're at different latitudes, so completely different solar irradiation or available solar power. And there you can see those 2 points there, a little bit better detail. And so I think these got cut off a little bit. I'm not sure if I can just, I don't know if that'll work. But if you can see down at the bottom of your screen there, we looked at the payback times. And unfortunately, the weight payback times got cut off. But for any of these scenarios, it's going to be different. Your payback time for a Afghanistan FOB could be as low as about a year, and it's closer to 5 years at these more civilian applications. You can see RES, that's a pure renewable energy system, and HRES there, that's your hybrid renewable energy system. And so typically your payback time for cost is going to be less with a hybrid renewable energy system, just because you are not paying as much for that for your solar panels and your energy storage. Kind of unfortunate, but if you want to download the slides, I know they're available there on the right. You can see the different payback times in terms of weight, and I actually specified them in terms of days. So your payback time for the Afghanistan FOB is only going to be right around 100 days for this Afghanistan FOB for logistics, and we're looking at about 150 days here for Puerto Rico, and for South Sudan, less than 150 days. And so in all 3 of those locations, in less than half a year, a pure renewable energy system is going to result in less total logistics that have to be transported to that location. So this is an important factor, whether you're at a civilian location or at a military location. If you're somewhere that's remote, obviously you want to transport as little as you possibly can. And something else I wanted to note is that while for payback times, we look at, in terms of cost, we look at a slightly better payback period when we look at a hybrid renewable energy system. When we're talking about logistics, pure renewable energy systems typically show better payback periods in terms of logistics. And the reason for that is when we talk about a hybrid renewable energy system, we are going to have to bring a significant amount of fuel, even if we're only going to run that generator 5% of the time. It's still a massive amount of fuel. And moving to the next slide here. Sorry, Daniel, I think I lost the ability to flip to the next slide somehow.
Yeah, hang on just 1 second, I'll get you back. There you go.
Okay, thanks. And as Daniel talked about, this is the paper that we published that kind of summarizes the research of what we're looking at. And so you can read that in the TME, the energy issue that was published in March. And so I want to wrap up by looking kind of back at that initial question that we asked and looking at what is the difference between a renewable energy system and a generator system. If we're looking at the first initial day of stand up, or say the first 30 days of operation, a generator and fuel is going to be much cheaper and require much less weight to be transported. But once we've operated that system for just 4 months, we start to look at, we actually have to transport more total logistics or weight because of all that fuel than we would with a renewable energy system, where the cost and the weight transported remain constant with time, with the exception of maintenance, which we've more or less neglected from this consideration, since when we're looking at a period of only a few months or a few years, your logistics cost or your maintenance cost is going to be insignificant compared to your initial purchase price and your fuel. But once we move to 2 years, not only are we transporting more weight when we talk about a generator, but we're also paying more. And that's looking at that 2-year payback time. But perhaps the most startling thing is at that 2-year point, we've now transported 7 times as much weight as we would have had if we had originally started with a renewable system. And so this just demonstrates how renewable energy systems can truly change the game in terms of mid and long-term logistics at a remote location. And this is really why we should be focusing on these more in the future. And I don't want to go into these too much in detail, but just wanted to state that basically our conclusions that we found is that we have reasonable payback times for both money and logistics in renewable energy systems. And your hybrid renewable energy systems are going to demonstrate lower initial cost and payback periods in terms of financial considerations. However, a pure renewable energy system is going to be superior to generators or a hybrid system in terms of long-term logistics. And we present an optimization model here that can be used to meet a variety of mission requirements using that logistics index. And from a midterm standpoint, in terms of both logistics, economics, and sustainability, PV renewable energy systems are competitive or superior to existing generators. And while they may not be optimum for every single solution, they definitely warrant further consideration. And I actually just want to go to this next slide here to talk about how this research could be expanded. something that we were not able to look at is how we could sort of automate our choice of PV module as well as your energy storage, in terms of if you pick a different location, say Puerto Rico versus Afghanistan, you might choose a different PV module. You might choose a different type of energy storage. It might not be a battery that makes the most sense there. And so it'd be nice to combine all those in sort of a analytical hierarchy process to make that determination. Additionally, we only used 1 year of solar data for each of these locations. However, with some Monte Carlo simulations, you could sort of expand that to deal with what's the uncertainty in these calculations. Homer software, which is used by a big portion of the civilian renewable energy system applications now, it could be ideal to implement this logistics optimization with that software. Unfortunately, Homer only optimizes for cost. And so it'd be great to be able to add a logistics optimization into that Homer software. And quantifying resiliency, as anyone will tell you, it's very tough to quantify resiliency, but it'd be ideal to compare that to existing generators. And then next, prototyping. We've sort of had experimental prototypes, but haven't pursued anything in the field yet that would be truly prime power scale. And on this slide here, you can see what one of those initial prototypes looked like. It was tested at home in Air Force Base, and we've tested some other things out at Kuwait, like solar shades, but nothing that's the prime power scale. I think these were 100 kilowatts instead of the 800 kilowatts that we wanted to look at with this simulation model. And so thank you for your time. And do we have any questions, Daniel?
We do. We have a lot of questions coming in, and do feel free to, if you've got some more questions, keep adding them into the questions chat. So let's dive on in here. So here's a question. It says, great presentation on some critical work, but how would the systems be able to sustain itself during a kinetic attack, for example?
That's a really good question, and I think that's an issue where you're sort of going to have excess capacity, just like you would with a generator. If your base power grid is dependent on generators, let's say you have 10 generators, they're spread out a couple different locations. Maybe one of your power plants gets hit, and you're going to have to expend resources and time to bring your other generators up and to fix the distribution system. And I think you're going to be faced with the same challenge if you're using renewable energy systems. If you've got excess capacity and say one of your solar farms or one solar panel gets hit, well, with that excess capacity, you'll be able to just take sort of offline that portion of the PV array and just continue operating with the rest of them. Part of it depends on how you set up your system, but you can sort of set up your system to be plug and play. And so for example, down here at Tyndall, we're testing it's a solar parking shade, and it's one of the few things that actually survived the hurricane. And it was actually right in our 9700 area. So only about maybe 100 yards from the ocean when it got hit with Hurricane Michael in 2018. It did damage several of the panels. But technicians were able to sort of disconnect and short through those panels. They just have quick disconnects, and so they were actually able to get that solar panel operating in really a short period of time relative to the rest of that area out there. That's at AFCEC here at Tyndall Air Force Base. So that's just one example of, just because it's a renewable energy system doesn't mean it's necessarily more susceptible to a kinetic attack than a generator.
All right.
Thanks.
So
this is Torrey Wagner. Am I able to add something to that question as well?
Yeah, we can hear you, Dr. Wagner.
Okay.
Thanks.
So this is something where, and I'm not meaning to endorse a specific commercial company, but there is a company called Armageddon, or a company that makes a solar cell called Armageddon that's fabricated in such a way that it can sustain perforation from small arms fire and have graceful degradation instead of the panel completely, the power output dropping completely. Additionally, if you have microinverters on each panel instead of string inverters, it's possible that if one solar panel gets destroyed, that you won't lose a sizable portion of your solar output, that you might lose it from just that particular panel. So in terms of fabrication of the solar cells and architecture of your system, there are ways to minimize the effect of kinetic effects on your power output. And that's all. Thanks.
All right, thank you. So we have a lot of great questions in here, Major Thomsen. And I know that we are at our 3 o'clock point here, but are you okay sticking around for maybe another 5-10 minutes or so? I want to get to a couple of these questions here,
yeah,
if that's
absolutely.
all right. Okay, great. Yeah, so this is our next one in here is about kind of along the same lines of kinetic attacks, but the relocating costs for it in a battle zone. Is there any? Did you look at this, or is this something you might consider as maybe an additional point of research?
What was that? You said the relocation
costs? The
costs?
relocating costs in a battle zone situation. Was that discussed?
So that isn't exactly something that we looked at in terms of how much is it going to cost to sort of take this down and set it up somewhere else. That is one issue where it's going to take longer to set up a renewable energy array than it would be to do so with say a single generator. The transport cost itself, we did have another thesis actually look at that, and it's approximately only 0.3 to 0.5% of your total cost. So less than 1% of your cost is going to be the transportation for this renewable energy system or a generator if you're transporting that. And so the biggest issue would be those installation costs. And potentially you can accomplish that with troop labor, but if not, that's going to be an additional cost that we didn't account for here. So thanks.
All right. Here's another question about some of the other potential costs. What about, for instance, non-functioning solar panel disposal costs in terms of recycling, toxic waste, hazardous waste disposal? Was that considered?
Yeah, that for the purpose of this study, that wasn't something that we examined either, but that is a good question. I mean, the same can be said for generators. You know, hopefully you pack them up and move them back so they can be used somewhere else. Same with these solar panels. Hopefully you can sort of pack them up at the end of a deployment and either sell them back to another company or to local industries. And possibly refit them for further use. But otherwise, if your goal is sort of to just abandon them in place, obviously there's going to be a cost to dismantling and disposing of them properly. And so that wasn't a cost that we looked at. So thanks for that.
Sure, yeah. And here's another question. For many military camps, losing power production for even 1% of the time is unacceptable. Did you look at the numbers using a more commonly found +1 generator configuration?
I hear exactly what you're saying, that just 99% power supply probability, if it's a mission critical facility, that's not going to be acceptable. But if we're looking at, for instance, a mission critical facility, that's when you're going to have a a backup generator, or you're going to have an up system somewhere like an air operations center or a command post. You're going to have a backup generator, and that's got to be the case even if you're operating on these prime power generators now. I don't know if anyone else has had experience being deployed, but pretty much everywhere I've been deployed, I've had the power go out. And it's sort of just a reality that you've got power grids that are potentially running hastily buried high voltage and other issues like that, and you just you're going to have issues, especially in a system that sort of has to be ad hoc developed as a base grows or shrinks. And so I would agree with you, 99% probability. Maybe that's not an ideal to shoot for a mission critical facility. However, we're going to have backup generation if we're talking about a facility where power is that critical. And that's where I would argue we're probably not going to want to move this in, say, the first day of a base that's operating. We're going to still be operating on generators. And so as you operate on generators, you can slowly replace those generators as you move more and more renewable energy in, maybe in that first 30 days to 90 days. And at that point, you'll still maintain some of those generators to be your backup. But thanks. Good point and great question.
All right. And then just to go back, we had one of our attendees who just wanted to expand a little bit about the first question about the panel vulnerability to kinetic attacks. He said, we found in Afghanistan in 2011, the PV panels were no more of a vulnerability than were soft-sided fuel bladders. They were protected by only a small berm. So just adding on to kind of what you and Dr. Wagner had talked about.
Yeah, thanks. Yeah, and that's a great point. It's sort of any sort of power system you're going to look at. You have your whole PV field, and maybe losing one panel or one array is really not a big deal. And whereas a generator, maybe if it's a single bullet that hits the right component of that generator, and that whole generator could go down. So there's definitely vulnerabilities regardless of our generation source. But yeah, thanks for that comment. That's really, really good point.
And I know there's a couple of other questions about cost, other costs such as long-term maintenance and such, which I know you touched upon in here. So in the interest of time, I wanted to kind of get to this one, which I think is a good one for perhaps you and Dr. Wagner to weigh in on. Based on your conclusions, what do you both see as the largest barrier to the adoption of renewable energy systems?
And Dr. Wagner, you might have a different thought. I think a lot of it is just, it's not what we're familiar with. We've been using diesel generators for years, and regardless of whether you're military or contractor, we've all focused on using diesel generators unless there's some sort of local power grid that we can tap into. And so to sort of change that mindset and start moving in renewable energy, we sort of have to be aware that we're going to have to add additional training and just additional knowledge that as the Air Force or if you're a civilian organization, it's something new that you're going to have to learn about. And the other reason I would say is just that solar has rapidly improved. 20 years ago, solar existed, but it cost, the cost was so much more substantial than it is today. And the quality, which still probably a long ways to go in terms of there's still room for improvement, but both quality and cost has improved immensely in terms of solar just in recent years.
And this is Torrey Wagner. I think I concur completely with Major Thomsen's assessment of that. Two other thoughts that I have are finding the right applications. Putting solar panels on an F-22 and hoping to have that fly through the air, I don't think is ever going to work. But lots of electric components are requiring lower power due to technology advances. Batteries are getting more energy dense, photovoltaics are putting out more power and becoming more efficient. So keeping an open eye for the right applications, I think, is critical to finding more applications for photovoltaics and battery storage in the DoD. And then I think the other thought that came to mind was force protection. That if you're in a combat zone and you have a very large solar array, it's not going to be hard to hit that with a mortar or something like that. So, and it kind of ties back to finding the right application. Over.
Well, thank you both for that. I know there's some questions that we just didn't have time to get to, but thank you, Major Thomsen, and thank you, Dr. Wagner, for staying on and answering a couple more here. So I just wanted to say thank you both, and thank you to all of our attendees who provided questions and attended today's webinar. If you haven't already, be sure to download the PDH certificate in the handout section before you go. And as Major Thomsen mentioned, you can also find the slide deck available for download there as well. If you have additional questions, you should be able to reach out. You can contact them about this research. And if for all of you who are interested in submitting an article to the military engineer, you can visit our website for our editorial calendar and our writer's guidelines. And after you leave the webinar, there will be a short survey about today's presentation. Please fill it out if you so desire. We greatly appreciate any and all feedback that you may provide. So on behalf of SAME, the military engineer, and our featured presenters, thank you for joining us today, and have a great rest of your day.
Thanks, Daniel. Thanks, everyone.